Good morning, everyone.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning.
So let's begin today's this thing. So in the last lecture, we were discussing about this. We have discussed actually about this different types of constraints, and while telling that, I was share my video. So can you see the screen? Hello?
Sir, the screen is blank.
Yes, sir. Dark screen.
Yes, sir.
It's totally black.
It's totally black.
Yes,
I'm
sir.
writing something. Can you see?
No, sir, nothing.
No, sir.
No, sir.
It's black.
Black screen.
No, sir.
Is it visible now?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Okay, so we were discussing about this rheonomic and celeronomic constraints. So as we said, rheonomic constraints are time dependent and celeronomic constraints are time independent. And I was discussing this problem. And you had a wire and a bead was sliding down along this wire. So bead moving without friction, right? And I said along with this is also rotating about z-axis with a angle of frequency omega, and this angle was constant. Okay, this angle was constant. So what I said was these constraint, this alpha is equal to alpha is constraint here, and I said this alpha is constraint. This is not time dependent, so it is time independent. So since this is time independent, I said that this is celeronomic, right? Celeronomic constraint. Okay. And since this, to specify the position of this, you can actually go through this. I mean, you can take the projection and for any instance if you want to find. So here I'm choosing my origin at this point. Okay. And this wire, or you can say rod, this is moving with angular frequency omega about z-axis. So you can see my video also, right?
Yes, sir.
Yes, sir. Yes, sir.
So if
Yes,
my
sir.
z-axis is like this, so this rod, if my z-axis is like this rod is going like this. Okay, this rod is going like this, and the bead is sliding on this, say, a rod or wire, whatever, stiff wire, frictionless. Okay, so about this z-axis, this rod is moving like this. So if I, at any instance of time, if I want to get the coordinates or to identify the position of this, so I can take the projection. So this angle I can take theta, and I can get the positions. Okay, so projection on x-axis and projection on y-axis you can get. Okay, and I said that this projection you can easily find out at x is equal to r sine theta cos phi, y as r sine theta sine phi, and z as r cos theta. Okay, now look here, if I take the projection, so at some instance this projection will make an angle say phi with the x-axis, right? But this wire is continuously moving, right? This is wire is continuously moving. So you have one more constant here. Okay, one more constant here, which is phi, which is moving with angular frequency, and also on. So at one time instance, you get this omega t. So with at t1 phi, this will make angle phi 1, right? At some another time, it will make another projection, right? So here somewhere, say after some time, it will go move. This time instant, it is here. So you get different phi, okay, depending on omega. And at another time instance, this will go here. You will have different projection, right? So you have one more constant here. Okay, this constant is time dependent. So this is again a constant. This is again a constant. This is time dependent constant. And time dependent constant, as I said, they are rheonomic. Okay. After that, what I did was, okay, so that point I actually missed. So if I want to write Lagrangian, so here this is my constant. I can use this as my constant. Okay, so I can change my origin. Okay, to simplify the problem. Simplify the problem. So what I did was actually I changed my origin from the top. Okay, so where the rod is or the wire is attached. So I fixed my origin somewhere here. So make it more clear. So this is my so this is x. Okay, but the origin is here. So what to write better? So this is 0, 0. My origin is here. Okay, rest everything is same. Alpha, and then you can see this bead is here. So this is my R. Okay, this is my R. And then if you want to, so x-axis 0, 0, everything is 0, 0 is here. In any way, if you want to find the x projection and y projection, you can draw the projection on x-axis and y-axis. Okay, this is there. So what is here is my phi is omega t. So I can write this x as r in terms of alpha and phi. I can write r is changing. R is changing. So this bead can be here, here, here. At any instance of time, r is changing. But alpha and phi is, they are constant. Alpha is time independent and phi is time dependent. So if I write this in terms of alpha and phi, so I can write this as cos phi, y as r sine alpha sine phi, right? And then z as my r cos phi. And then I put my phi is equal to omega t, this constant. So if I write x dot y dot z dot, so instead of phi, I put omega t. Okay. Instead of phi, I put omega t. So my x dot will be r dot. R is time dependent, right? R is time dependent. Alpha is time independent. So it will remain as it is. This will cause the first derivative I'm taking with respect to r. So this will remain as it is, or you can write omega t here. Now derivative of this, since alpha is constant, first term will remain as it is. Derivative of cos phi with respect to time, and omega phi is my time dependent, so I can get omega sine omega t and then sine alpha. So this was what we derived yesterday. Okay, similarly you can find out for y dot and z dot. Okay, and then you can write Lagrangian as I said, half m x dot square plus y dot square plus z dot square minus mgr cos alpha, so that you can get it. Okay, and from here equation of motion. Is that clear? Who was that girl yesterday asking? Is it clear now?
Yes, sir. Yes, sir.
Okay. So today we will derive this, how to get this equation of motion. So our ultimate goal is to get equation of motions, right? So far we have been writing this equation of motion, Lagrange's equation of motion, that d dt of del L by del Q minus del L by del Q dot. Okay, so is equal to 0. So we are writing this, but so far we don't know how they are coming. Okay, so today we will try to find out how they come. So it basically comes from your Hamilton's principle. Okay, Hamilton's principle. Hamilton's Okay, so what is Hamilton's principle? So it basically we have to go. So I also told you about little bit about configurational space. As I said, this configurational space need not have any necessary resemblance or direct, you can say, resemblance with your real life space, okay, or real space. So whatever actual path is there in your three-dimensional coordinate space may not resemble exactly same as in configurational. So it is not necessarily that configurational space, whatever curve you see in configurational space is same as in your real space. Okay, so to remind you again that we have said that in our normal coordinate space, you have x, y, z, and to represent any point, we write x, y, z, this set of 3 points, right? But what do we do in configurational space? In configurational space, instead of writing this x, y, z set of points, we use each coordinate as one dimension. So in configuration space, we define these coordinates by q1, q2, and q3, and this represents. So this is three-dimensional space in your generalized form or generalized coordinate system. So it need not be having, suppose n particles, then you will have 3n coordinates like q1, q2, q3 up to these 3n coordinates. You can write q1, q2 up to n. Okay, where small n is your capital 3n. Okay. And then when the system, the complete system, if you have n-dimensional n-particle system, if it is moving here with some time, it may trace some path. But what we do here is we system. So all the n dimension we cannot draw n-dimensional space. Qn, and on this axis is t. So how it changes, the whole system changes with time. It will trace some path. Okay, and each point on this path, each point on this path represents one state of the system. Okay, one state of the system. So that is there. So with this background, we will try to see how we can get equation of motions using this Hamilton's principle. So what Hamilton's principle describes, it describes the motion of the mechanical system for which all the forces are basically derivable from some generalized scalar potential. Okay, so you might have read in your BSc also, there are forces, if they are conservative, you can write in terms of some scalar potential. So if you have force, some blah 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 force, and if it is derivable, you can write this force in terms of some scalar potential, some gradient of v, this potential, or gradient of phi. Okay, so these scalar potential you can write these forces if they are conservative, and if they are, so this potential may have dimension of sorry, I should not say dimension, but they may be a function of distance, they may be a function of velocities, or they may be time dependent. Okay, so they can have variables x or the distance, time, or velocities. Okay, they can be anything. Okay, and important is if they are only distance dependent, and if they are conservative, then these systems are called as monogenic systems. So what we are saying is monogenic system. Monogenic systems where the potential, where this potential is an explicit function of position or distance only. And along with that, the monogenic system are also conservative. Okay, so this is basically monogenic system, and we are applying this Hamilton's principle to these monogenic systems. So what we are saying now is what Hamilton's principle tells you that if you have such monogenic systems, and if you take a line integral over this, whatever system follows the path, or the whatever action is taken by the system of particle, or your whatever mechanical classical system you have. Okay, if this system has this line integral, okay, line integral, so between 2 points, say time frames, so t1 to say t2. So if this line integral t1 to t2 is like this, okay, if this line integral have the stationary values, okay, so what we are saying is that for the monogenic system, if your system is going from one state to another state, okay, in time interval t1 to t2, if this state of the system which is moving from one frame to another frame, if it has the stationary paths, okay, stationary paths means what? So say from this t1 to t2, okay, it will follow the least possible path, you can say. Least possible means from between these 2 points, it can go like this, it can go like this, it can go like this, it can go like this. There are many ways this system can go from one point to another point in this time frame, but it will always follow the uh, least possible path. Means it may take a least time, it may take a least distance, or it may take a least velocity, least time or distance. Okay, so this is the general, basically the principle of Hamilton's, which comes from your variations, calculus of variations. Okay, calculus of variations. So this is the basic definition. So if it has a stationary values, so it cannot go from stationary values, means from the nearest neighborhood. So if you try to get the nearest neighborhood, the least stationary values will, it cannot vary, basically it cannot vary from its least possible value. So if you take a nearest neighborhood, then it will always have a value greater than that. It will always have a values greater than that. So a system will travel from one point to another point with all its states, with the least possible path. Okay, it cannot go like this or like this. If you try to go like this will have variation. Variation means it will have the highest values. So this line integral should have stationary values, and that stationary value can go only through this least possible path. Okay, that is in words you can say the mathematical in words I can say that this is the Hamilton's principle. So we basically want to show this, and we will show this through this calculus of variation. Famous way of showing that is through the calculus of variation. So in other words, you can say that this is true. This is true that there is no other variation possible. Okay, so if you try to go from this path, if you try to go away from this path, okay, so say any delta variation you try to follow. Okay, suppose that your system is going through this any delta variation away from this least possible path, then what will happen? It will have a non-zero value. Okay, non-zero value. So if I want to say that this Hamilton's principle in other words, then what you should have is variation in your delta I over between these 2 points T1 and T2 should be like L T1 and T2. This LDT must be 0. Okay. So again, the same thing, what I said, if your system is going from one state to another state, in between the points T1 and T2, if you try to take the variation in that, delta variation, any smallest delta variation, then this delta variation, okay, will be 0 if it is, and if it takes some value, that means this is not the least possible path. So only path possible is this, the smallest possible path. Okay. So this is the another way of saying that the variation in the line integral, okay, must go to 0. Okay, must go to 0. So this Hamilton's principle is the necessary and sufficient condition for our Lagrangian. So here L, as I said, we have Lagrangian is a function of your generalized coordinates and generalized velocities. So you write Lagrangian in the form of, these are your QIs. QIs are your generalized coordinate. We have already defined generalized coordinates. The number of coordinates required to completely specify your system. Okay, these are generalized velocities. And then you have a time parameter. Okay, you have a time parameter. So Hamilton's principle is your necessary and sufficient condition for your Lagrange's equation. So it can be shown that Hamilton's principle followed directly from Lagrange's equation. However, what we will do, we will prove the converse of it, that we will show Lagrange's equation follow from Hamilton's principle. Okay, and this basically forms the basic postulate of our rather than your Newton's law of motion. So in my first lecture, I said that what we say a law is which is not derivable, or not derivable. Derivable means you cannot prove it, right? You cannot prove it. But Newton actually, before Lagrange's also, he said that these are the laws which are followed in nature, and that's why we call them law. But actually, they are not law. In principle, we can derive this law in more general way. What we are going to see, the same what we wrote, ddt of del L by del Q dot minus del L by del Q equal to 0 is nothing but Newton's law. Okay, in a more generalized way. So that's why we say that now these Hamilton's principle form the basic postulates for our laws of motion, or they are basic postulates rather than Newton's laws of motion are the basic postulates. Okay, so we will do this in more general way. So we will try to show this from calculus of variation, calculus of variation. So our main aim is to find the integral, and for that integral, the variation, if I try to get the variation, that variation should be 0. So we choose a function. We choose a function. We choose function. Okay, function is such that f is a function of y dot x. Okay, defined. It is defined by a path. Okay, so this is not a function. Actually, this is called functional. I'll come to this again. So this where this y is y of x. Okay, between uh, points x1 and x2. So this is similar to our previously what I have drawn. So you have qi's and you have t, and I was trying to go from time t1 to time t2. So here I have a functional. Okay, say I can write y and x. Here x is playing the role of t. In this case, your x is playing the role of t, and qis is played by this y. Okay, these are all qis. Okay, and it is following some. So here uh, your L was following that, and here f of x, y equal to y of x is following that path. Okay, it is following that path. So what is our aim? We want to find the path y of x such that the line integral j of the function f between x1 and x2. So what is our aim? We want to find this line integral j, okay, between the points x1 and x2, such that f of y dot and x dx. We want to find this j such that this line integral has stationary value. Okay, stationary value. That is our aim. So here y dot is nothing but our dy by dx. Okay, here y dot. So here y dot is my dy by dx. Okay, y dot is my dy by dx. So this quantity f, okay, this quantity f depends on the functional form of what the dependent variable, you can say y equal to y of x. Okay, this functional, it depends on the functional form of y equal to y of x. Okay, so it depends on this y equal to y of x, and this f is therefore called as, it is not a function but it is called as functional. Okay, this is called as functional. Okay, functional, not function. Okay, because again this y depends on y of x, right? This y depends on y of x. In general, what we are doing is, this is my y, this is my x, okay, and this line integral is this, so x1 y1, x2 y2. Here your x is playing the role of t, so we want to find that any variation from this path is not allowed. So here, very important point again, whatever variation we take, if I take this variation, this passes through these endpoints. Okay, so this y equal to x1 equal to y1 and y equal to y of x2 is y2. So if this is my real path, okay, if this is my real path, and if I take any variation from this path, this varied path must pass through these endpoints. Okay, and the derivative of at that point, okay, is zero at that endpoints. This is the basic condition here. Even you can vary this x1 and x2, but for that case, then again, instead of finding only y of x, you will also need to find x1 and x2. Okay, but we will not go into details of that. That is again a different approach. So for our case, these two endpoints, x1 and x2, they are fixed, and any variation path you take on this, they are again any varied path will pass through this endpoints. Okay, any varied path will pass through these endpoints. So to prove, let us consider the nearest neighbor path, as I chose like this. Okay, you can choose a nearest neighbor path. You can choose. So there are infinite number of paths you can choose between x1 and x2, but what will show that this will follow the least possible path. Okay, least possible path. So let's take the nearest neighbor path with a variation or the infinitesimal variation, you can say, a parameter of with alpha. Okay, so there is a variation in your path. Okay, and that variation, the very small variation, I denote it by alpha. So let's take variation by some infinitesimal parameter alpha. Okay, and such. So this is my y equal to y of x. So what we are saying is that I have defined a function y is equal to x alpha. This is my varied path. And what is my actual path? The correct path at which alpha is 0. Okay, this alpha is 0. So y x 0 is my actual path. Okay, and I'm going from this actual path to the varied path. Okay, and again I define a function which is variable having x. Okay, so I choose eta of x. I choose eta of x that vanishes at your x1 and x2. So what I said that whatever my actual path is there, I can choose a varied path with a parameter alpha and a function eta of x. But the main condition is that this varied path must go through these endpoints, this x1 and x2. The varied path and the actual path should pass through this x1 and x2. So if I write this varied path, I can write this varied path, a function, okay, is like y of x alpha is equal to my actual path x0 plus how much it has varied from my actual path, that alpha eta of x. Okay, alpha eta of x. So we have this condition, and we assume that this y of x and eta of x are well behaved. So well behaved means they are continuous, non-singular. Okay, I mean the first derivative, second derivative are lies in between this x1 and x2. Okay, so there is no discontinuity, etc., in this in between these x1 and x2. So they are well behaved. Okay, so if this is true, then what is my Hamilton's principle for this varied path? So I can write again that varied path line integral between x1 and x2 as f of y of alpha x alpha and y dot of x alpha x px. And to obtain the condition for stationary values, so by basic definition, you know the stationary values. If you take the first derivative of this, so stationary values, they were, as I said before also, so if you have some function which is varying somewhere like this, so if you take the derivative at this, the values are constant. So we call these as stationary values. Okay, the first derivative shows maxima or minima at this point, the nearest neighborhood point. They have the stationary values. Okay, so for our case, this j of alpha, you can say, varying from x1 to x2, f of y x alpha, y dot of x alpha, and x dx. Okay, to get the condition of stationary, we should have tj of t alpha should be equal to 0 at alpha equal to 0. Right? This is condition for obtaining stationary. Right? So if I take derivative of this with respect to alpha, so your dj by d alpha would be x1 to x2, del f by del y by del alpha, plus del f by del y dot by del alpha dx. Right? Now I will consider only this second part of this. So just write it as, say, this p. Okay, so this p is nothing but x1 to x2 del f by del y dot by del alpha dx. So I can, and y dot is my del y by del x. I have written this del y by del x, so I can write this as x1 to x2 del f by del y dot. This is del 2y by del x del alpha dx. Right. So I apply integration by parts on this part. So if I do so, what I will have is integrating by parts. So if I do that, what do you have? So you can write this. If I take integration of uv dx, you will have u integration of v dx, and then minus integration of derivative of this du by dx to integration of v dx and dx, right? So here my u is this and v is this. So if I apply that, you will have del f by del y dot integration of x1 to x2 del 2y by del x del alpha dx minus x2 dx del f by please, what has happened? Okay. So here, okay, let me do it on another page. Okay, so I am integrating by parts. So what you have is del f, oops, del f by del y dot and integration of x1 to x2 del 2y by del x del alpha dx minus x1 to x2 ddx of del f by del y dot integration of del 2y by del x del alpha dx and then dx. This. So if you solve this, you will have del f by del y dot del y by del alpha between x1 and x2 minus x1 and x2 dx of del f by del y dot into del y by del alpha dx. Okay, so what is our condition? Basically, what we said that the varied path is passing through these endpoints. Okay, you are not allowed to vary this x1 and x2. So they are passing through this endpoints. So your actual path is this. So from wherever this actual path is going through this x1 and x2, from there only this varied path is also passing. So these two endpoints are fixed. Okay, so there is no variation. So what we are saying that there is no variation in this at this endpoints also. Okay, so whatever the actual path is there, from there only this varied path is also going through. So if this is true, then this term will vanish. Okay, this term will vanish. So this will become 0. So ultimately, what do you have is this term, right? And then this part I will substitute. P here. Okay, this P here. So this what we are getting is this is my Okay. So if you check there, this is dj by d alpha, which is del f by del y. Del y by del alpha is there, minus this whole term. Okay, so minus this whole term. So if I write, therefore, my dj by d alpha would be x1 to x2. You have there del f by del y and del y by del alpha. Okay, and minus this term. So you have ddx of del f by del y dot del y by del alpha dx. So if you take out this x1 to x2, del f by del y minus ddx of del f by del y dot, and I take out these two terms common, so del y by del alpha dx. Okay, del y by del alpha dx. So dj by d alpha. So for my stationary condition, you should have this dj by d alpha should be 0, right? That means my this term should be equal to 0 in order to have the stationary value. Okay, in order to have the stationary value. So now if I see what is my del y by del alpha, del y by del alpha is a function of x. Okay, and that we have chosen arbitrary function, right? This is any arbitrary variation from your actual path, right? So except that these endpoints are fixed. Okay, so this eta x into alpha, this is my arbitrary anything. Okay, so arbitrary function. So these two things what we have gotten here, this part and this part, it is, so this del y by del alpha is basically coming from this arbitrary variation we have taken in the nearest neighborhood of our actual path. Okay, so there is one lemma again from the calculus of variation. If you have such arbitrary function around your another function, so that lemma tells you that there is a lemma variation between x2 and x2. If there are two functions like this, dx equal to 0, so for all arbitrary functions, eta of x, okay, eta of x is continuous through the second derivative then m of x must identically vanish in the interval x1. Okay, so what does that mean? So this is like they are independent of each other. Okay, so if they are independent of each other and the quantity is 0, that means they should be independently equal to 0. Okay, so if this is true, since eta of x is independent of h of x, and since this is independent to this, they are independently must go to zero. Okay, and since this is true, your quantity in the previous bracket, so this whole quantity is your m of x, this is eta of x, they must be independently equal to 0. So if they are independently equal to 0, that means your this quantity del f by del y minus d dx of del f by del y dot should be equal to 0. Okay, and if you see it carefully, so this is your Euler-Lagrange. So this is your Lagrange's equation of motion. Okay, so this was first proved by Euler. Okay, Euler. So here f is a function of y dot and the parameter x. So your Lagrangian is a function of q dot and the parameter t. Okay, so here y is q, y dot is q dot, x is t. So if you write this in this form, so you can write it as del L by del Q minus d dt of del L by del Q dot equal to 0. So this is called as Euler-Lagrange equation of motion. Okay, this is Euler-Lagrange equation of motion. So this came from basically from your variational calculus of variation. Okay, so do you have any doubt so far? Any doubts?
Sir. Yes, sir.
Ah,
Said that integration x1 to x1 to x2 h of x eta x dx equals to 0. This can be implied that any of one can be 0.
sorry,
Then,
can you speak it loudly? Speak a little loud.
yes, sir.
Ah.
Am I audible?
Yes.
Said that h of eta of x dx equals to 0 implies any of them could be 0. Then we have taken only h of x as a 0. Why is it so?
They are independently 0. They are independently 0. They must be independently 0.
Okay.
They must be independently equal to 0. I am not saying one of them is 0. They should be independently equal to 0.
But it can be possible, na sir? Any one of it will be 0.
No. That is the basic lemma.
Okay. Okay, sir.
Yes. Any other question? So if there are no other question, then we'll stop here for today. And then again, day after tomorrow, we'll meet. So should I stop meeting?
Yes, sir.
Yes, sir. Yes, sir. Thank you, sir.
Yes, sir.
So this is very important. You go through it once again. Okay, then. Thank you for today.
Thank you, sir.
Thank you, sir.